Think of vectors as the new world of mathematics. The new world with some familiar names, but with things working slightly different.
In an earlier section, we studied a few vector operations, such as adding and subtracting, and multiplying vectors by numbers, which is called scalar multiplication. If we take the vectors u and v and add corresponding components, I've got those color-coded for you, we get the vector u plus v. If we subtract corresponding components, we get the vector u minus v. If we multiply the vector u by 2, that means we multiply each of the components by 2. And if we multiply the vector v by negative 3, we multiply each of the components by negative 3. Now, those operations may lead us to believe that we have such a thing as vector multiplication, such as u times v. There's no such thing. There is, however, a couple of operations that are defined for vectors that resemble multiplication. So we actually call those the dot product and the cross product. These aren't actually multiplication of vectors. It's just some new operations that sort of resemble multiplication, so we borrowed the word product to go with them. Now, the definition of the dot product for two-dimensional vectors looks like this. Notice that in the dot product, we are indeed multiplying corresponding components. However, we're also adding those together. Here's what it would look like in 3 dimensions. And of course, the sentence I put in here is extremely important. In the dot product, the answer is not actually a vector, it's simply a quantity, a number.
Now, here are two three-dimensional vectors, u and v. The dot product of u and v, again, simply means multiply corresponding components and add. 2 times negative 3, 9 times 1, negative 1 times negative 4, all added together. And this is an easy enough operation to do without any assistance from the calculator. However, the TI-89 has built in a function called DOTP, which you can get through the catalog or simply by typing the letters DOTP. Now let's look at this interesting dot product, the dot product of a vector with itself. Now here's a vector, 3-component vector, 3-dimensional vector, and to dot it with itself, you simply multiply the first component and the first component, which means the first component squared, second component squared, third component squared, all added up. Well, this is an awful lot like the magnitude of a vector. In fact, you'll notice the magnitude of v is the square root of that sum. And the square root squared would give you v1 squared plus v2 squared plus v3 squared. And so the dot product of a vector with itself is the same as the square of the magnitude of the vector itself. Now, like before, you might want to make you a copy of this screen. You can print it off from the slides, I think. And the idea, of course, is this is a lot like what we learned back in beginning math. The commutative property, one at the top, simply says it doesn't matter what order you do a dot product in. And then, of course, the second one is almost identical to the distributive property, for real numbers. And the associative property is practically identical. Just replace the dot with the times sign and it would look the same. The fourth one is the one we just got through talking about. Notice in the last one, you've got the 0 vector dotted with the v vector, which comes out to be the quantity 0, not the vector 0. Now here's an interesting relationship I want to show you that relies on something that we learned back in trigonometry, that being the law of cosines. If we construct the vector v minus u across between the points of the u and the v vectors, then from trigonometry, the law of cosines tells us that the sum of the squares of the two sides beside the angle theta minus the quantity 2 times u times v times the cosine of theta is equal to the square of the side across from the angle theta. You can go back and look that up in the trig book if you need to. However, I'm going to do a little algebra on this. On the left-hand side, we got the magnitude of v minus u squared, which is, we just got through seeing, the dot product of v minus u with v minus u. Well, using the distributive property twice, we come up with this. Now, the u minus v, the u dot v and the v dot u are the same thing. So that means we've got 2 of those. And so we will call that 2 u dot v's. So we'll replace the magnitude of v minus u squared with this. And some things we'll subtract out and divide out. And we get this nice little interesting relationship, which is very important. Another description or definition of the dot product of u and v is the magnitude of the two vectors times the cosine of the angle between them.
Now, our new formula for the dot product is nice, but one of the best things about it is we now have a way of finding the angle between two vectors. If we divide this through by the magnitude of u and magnitude of v, we get an expression for the cosine of the angle between the two vectors, which we can do the arc cosine of to find the actual angle between those. Now, I put on here a program that I use on my TI-89 to do that calculation quite quickly.
So for these two vectors, we can find their dot product. That would be -1 times 4, 3 times -2, and 5 times 0 added together. And the product of their magnitudes, magnitude of u being the square root of -1 squared plus 3 squared plus 5 squared, magnitude of v being the square root of 16 plus 4 plus 0. And so that comes out to be approximately 112 degrees. Now the little program that I had that does this on the TI-89, you just type V angle, then the two vectors, and it gives the angle in degrees. Now an interesting fact to keep in mind is that if the dot product happens to be 0, then the cosine of theta equals 0 means the theta would have to be 90 degrees. Now that's a special relationship between vectors that comes up quite a bit in dealing with vectors. We have several names that we'll use for this, but the one that's referenced right now is the word orthogonal. That just means two vectors that are at 90 degrees to each other.
Direction cosines, or direction angles, are used a lot in science and engineering And let's take a look at what that means. Here I've written an expression, v dot I, which according to the definition that we just came up with is the same as the magnitude of v times the magnitude of I times the cosine of alpha. Now the I that we're talking about here is the vector I, the unit vector that 1 unit long and points along the positive x-axis, which means that the alpha that we're talking about here is the angle between the vector v and the positive x-axis. So let's do a little algebra here. If we do the dot product and then divide both sides by the magnitude of v, we see that the cosine of alpha is v1 divided by the magnitude of v. Now we'll kind of save that and do the same thing here with vector v and the vector j, which is the vector 1 unit long that's pointing along the y-axis. So therefore the angle we're talking about here, called beta, is the angle the vector makes with the positive y-axis. We'll do the similar algebra on this. And then the third one, we'll use k, which is the unit vector pointing in the direction of the positive z-axis. And that gives us the angle gamma between the vector and the positive z-axis. And again, we can solve that. Now these are what we mean by vector, by direction cosines.
So if we want to find the direction cosines for this vector, we would simply use the formulas that we just came up with. First component, 2, divided by the magnitude. That would be the square root of 2 squared plus 3 squared plus 3 squared. That would be 4 plus 9 plus 9, which is 22. And so 2 divided by the square root of 22 is the cosine of alpha. And the cosine of beta, the angle between the positive y-axis and the vector, would be the second component divided by the square root of 22, and the cosine of gamma would be the third component divided by the square root of 22, which in decimals would be this. Now, of course, these are radians since we're working in units, not degrees. Now here is the program from the TI-89 that finds the direction angles for alpha, beta, and gamma. And you run the program, dir angle, and then type the vector, you'd get the 3 angles in degrees.
If we take these 2 vectors and shine a light so that it's perpendicular to the vector v, then the shadow that the vector u makes on the vector v is called the projection of u onto v. It even works if we shine the light and vector v is going in the opposite direction. We just have to think of our vector w going in the opposite direction. That is referred to as proj subscript v and u. Now look carefully at this, because this is saying we're projecting u onto v.
Okay, now we're going to take the angle between the vectors u and v, and we're going to remember that the cosine of the angle, look at the little right triangle, is the magnitude of the w divided by the magnitude of the u. We're going to rearrange that, and then just recognize that a unit vector in the direction of v, that means a vector 1 unit long, would be v divided by the magnitude of v. And so w would have to be the magnitude of w times the v divided by magnitude of v, the unit vector in the direction of v multiplied by however long you want the vector to be, which is the magnitude of w. So to make our little equation up here look like that, we're going to multiply both sides by v over magnitude of v. So the left-hand side becomes just the w. That's what we're looking for. And the right-hand side is basically what we want, only we're going to make it a little different looking, although we could use that formula. It'll look a little nicer like this. We're going to multiply top and bottom by the magnitude of v. Now the top, you'll notice, is the dot product of u and v. So we'll replace that with u dot v. Now again, the important thing about this is to remember that this projection of u onto v is always some multiple of v. Now that multiple happens to be the dot product divided by the magnitude squared. Now I'm using completely different letters in the example just to illustrate it's not what letters you have, but what's projecting where that's important. So if we're going to be projecting A onto B, that means our formula has to have something multiplied by B. That would be the dot product divided by the magnitude of B squared. And so again, we just do all of those calculations. And we get the projection of A onto B, which is this vector. Of course, I have created a program that does that. It's nice and simple.